Thank you. So thanks a lot for the invitation and to the organizers for giving me the opportunity of presenting these three lectures. So my idea is to present some subjects which are well known in gauge theories and have been very interesting in the context of gravity in the last years. So the idea is to talk about instantons. So this is an introduction, of course. Introduction to instantons. In gauge theories. And gravity. And so the plan of this is, so today I will talk about very general things. Perhaps some of you will get bored during the talk today, but I will talk about some gauge theories. And in particular, topological solitons, which are, some examples are monopoles, instantons. I don't think that I would have enough time to talk about metals and other kind of topological solitons, but perhaps monopoles and instantons would be enough. On Wednesday, I will talk about some applications of these topologically non-trivial solutions in the context of anomalies. So in particular, I will talk about the axial anomaly. And finally, on Thursday, my idea is to present gravitational instantons in ideas. Okay? So for the students, please feel free if you would like to ask in Spanish. There is no problem at all. Okay, but I will give these lectures in English if someone doesn't speak Spanish at the audience. So we know that gauge theories are the best description that we have of interactions in nature. And there are different and very interesting phenomena that occurs in gauge theories that are non-perturbative in nature. And for instance, tunneling, superconductivity, and a lot of very interesting phenomena are described by configurations which has non-trivial topology, like vortices, solitons, monopoles, and instantons. In the context of gauge theories, like in particle physics, the presence of instantons induces, for instance, in QCD, an additional term, which is known as the theta term of QCD, that it can be written as a locally as a boundary term, so it doesn't modify the dynamics of the gluons. However, at the quantum level, it modified some observables that you can go to the lab and measure, like the electric dipole moment of the neutron. And you can go to the lab and see, this extra parameter that appears in the QCD Lagrangian will give me a contribution to the electric dipole moment. And then you go to the lab and you don't see any dipole moment electric dipole moment of the neutron whatsoever. And so this imposes super tight constraints on the theta parameter, and this is known as the strong CP problem. There has been plenty of solutions to this problem that is non-perturbative in nature, and different, coming from this proposal, different particles can arise as, for instance, possible candidates for that matter. This is the case for the axion, for instance. So, in different cases, we have that either monopoles, instantons, skirinos, and other kind of solutions with non-trivial topology are super interesting in the context of physics in general. So, my idea is to present some of them and applications thereof, like in the case of anomaly. Anomalies are symmetries that are preserved at classical level but are broken at the quantum level. And this is what happened in the case of the axial symmetry of massless Dirac fermions, where if you consider the path integral for Dirac fields, you will see that there is an additional piece that comes from the non-trivial transformation of the fermionic measure. This is something that I will discuss on Wednesday, and hopefully I will give you some details about how the computation is done. And in the context, and since gravity can be thought of, at least in the Euclidean signature, gravity can be thought of as a gauge theory for SO4 group, or can be thought of in the Lorentzian as a gauge theory for the Lorentz group. It is supernatural to ask whether these solutions exist in gravity as well. And I will show you that there is a lot of similarities between some configurations in ideas. These are known as gravitational instantons, which are pretty close to the ones that I will present today. Okay, so this is the motivation and the a sort of a plan that I will try to do if I have enough time. So let us start with generalities in gauge theories. And let us introduce the connection. So gauge theories in general is a technical topic. So I will try to keep technicalities for more advanced lectures. But now I would like to give you some insights about the physics of gauge theories. But the idea is that in general we have fields which will represent matter fields. Let's say, let's call it psi, a matter field. In some representation of a Lie group G. So, let us consider an element X be an element of this group such that this matter field transform under the action of this group like this. So this is the standard transformation under an element of the Lie group. Okay? And so since this is an element which has an explicit dependence on the coordinate of the spacetime, the covariant derivative of this guy won't transform in the same way as the field. Okay? So this is something that also...
Why does it have to transform in the fundamental?
It doesn't in general. It could be actually a scalar, it doesn't transform at all. It could be also a field that transforms in the adjoint representation as well. The adjoint will mean that you will have a u to the -1, u from the right. And yeah, it doesn't have to transform in the fundamental in general. So this is just a particular example, but you're right. It could transform in any other representation of the group. Right. And this is important what Ignacio is saying, because we will see that the gauge connection will transform in the fundamental representation. Will transform as a connection, but in the fundamental representation of the gauge group. So it is easy to see that. What about the derivative of this guy? And it is easy to see, since the transformation depends on the coordinate, that the derivative does not transform covariantly. This will be ux psi, and then you will have the u psi plus. So this piece spoils the transformation of the derivative under the transformation u that belongs to G. So I don't want to bother you with all of this, because some other colleagues of mine were explaining this during the day. But what we usually do is to introduce a compensating field. And this is known as the connection that cancels the extra pieces, the non-homogeneous pieces coming from the derivatives of this element of the group T. So we promote to solve it, to fix this. We promote to a covariant derivative, which is the standard partial derivative plus a connection. And we demand some particular transformation for this connection such that it cancels this piece. Okay? I will avoid the details, but the idea is you have this, you will transform both the field and the connection inside, and we demand that this should transform covariantly. So what I mean with prime on the left-hand side outside of the parentheses is that I will take T mu plus a nu prime psi prime, and on the right-hand side you will have D mu plus a nu u psi. So playing with the u elements, in general u can be matrices. So you use that, of course, u minus 1, u is the identity, u minus 1, same thing. And at the end of the day, you find that this guy transforms in this way. This is the standard piece of a field that transforms in the adjoint representation, plus an additional term that cancels the non-homogeneous transformation of the derivative. And this is u to the minus 1. Okay? So this is the transformation law that the gauge connection should follow such that the derivative transforms covariantly under the action of the D group G. Okay? When you're considering, if you have a connection which only has the second piece, then you will see that this leads to a vanishing field strength. But to talk about the field strength first, I have to define the field strength. And so, what the field strength of curvature is, just to take the commutator of two covariant derivatives acting on psi, and then you will see you just act twice, change mu by nu, and you will see that this is mu where mu minus a mu plus and as Alberto was saying in the morning, in general these guys are valued in the Lie algebra of the group, so they can be A could be a matrix. So in general we have this commutator here, and in some cases the commutator just vanishes, like in Maxwell theory, that we will see. And so there is homework that you can do. If you take a particular connection, which is just this piece, then F nu vanishes. Okay? Thus, one. Show that if a mu is the last piece, then F mu is equal to 0. And this is called a pure gauge connection. Okay? There are interesting things that F mu satisfy. I will discuss a particular condition that we will be studying through these 3 lectures, which is self-duality. But first of all, there is another, let's say, identity that this tensor satisfies, and it is the Bianchi identity. Bianchi identity, which is if you take the gauge covariant derivative, that one, antisymmetrized with F lambda rho, this is equal to 0. In the adjoint representation, we'll put it here, in the adjoint representation, which is, for instance, the representation of the gauge potential, the covariant derivative goes in this way. It goes like the partial derivative plus a commutator, a mu, comma, and then here in the dot you plug the object that you would like to differentiate. Okay? If you are taking F nu, so since F nu is also in the adjoint representation, then you need to consider the commutator acting on this. Okay? And for fields in the fundamental representation, you take this definition. So, last thing I have to say about generalities in gauge theories is self-duality. And self-duality is a property that Maxwell field equations have in vacuum. Okay? It is sort of the covariant version of the electric-magnetic duality that you learn in electromagnetism. Written in this way, first of all, we need to define the dual field strength. So the dual field strength is defined, and I will call it with a tilde, and it will be 1/2 is the Levi-Civita tensor lambda rho f lambda rho. And we call that in general, since the gauge connection, no, this is something that I will clarify later, because otherwise it would be a bit misleading. But bear in mind that in general, the gauge connection is contracted with the generators of the Lie group. So in general, they are matrices, okay? And so F mu nu will be Lie algebra valued as well. And in this case, if you define the dual field strength in the following way, there are very interesting properties that these fields satisfy if the gauge potential is self-dual. What that means, let's say anti-self-dual connections implies that the field strength is equal to plus or minus, plus for self-dual, minus for anti-self-dual, it's dual. If this condition is satisfied, then we say that the gauge connection is self-dual or anti-self-dual, depending on the sign. Okay? So keep in mind, I will be using sometimes differential forms. And so, in general, if the Lie group G has a Lie algebra, call it like matfrak G, which is spanned by the generators T satisfying the Lie algebra put it in this way, TA, TB, FA, B, C, TC, where these are the structure constants of the Lie algebra. Then I can define the gauge connection 1 form, which will be, in general, an object which has one index on the spacetime, another that it is valued in the Lie algebra, let's say C, and it is contracted with the generators. So in general, these guys are matrices, as I was saying, X mu. So this is a 1 form, which is valued in the Lie algebra of the Lie group G. And the field strength, in this case, can be defined as the exterior derivative of A plus 1/2 the commutator of these two guys. Then you work out the commutator, and then this can be written as dA plus A wedge A. And this is what Alberto wrote in the morning. Okay? So sometimes I will be using the language of differential forms, and at some point it is more useful to use tensors. Okay, so let us work out an example of this. And a very nice example, which is a well-known theory by all of you, is electromagnetism, that can be thought of as a gauge theory for the U1 group. Okay? And I will present some, hopefully, some interesting and topologically non-trivial solutions in Maxwell theory. Any questions so far?
Cristóbal?
Yeah.
A basic question.
Right.
What do you mean about the self-dual? What is dual the concept of the fields?
Yeah. So first, in order to define self-dual, the self-dual condition, first you need to define what a dual of a field of a tensor is. So in this case, dual is defined as the first line above. So it is just take the field strength, your non-abelian field strength, and contract it with the Levi-Civita tensor. This will be the your dual field strength. And then on top of that, so this is the definition. If you have a particular configuration that satisfies the condition below, we will say that this is a self-dual or anti-self-dual configuration. So self-dual means that the field strength is equal to its dual. And anti-self-dual means that it is equal to minus its dual. Okay? But there are very funny things that happens when this condition is satisfied. Okay? All right. So let us consider Maxwell theory. So Maxwell theory is a gauge theory for the U1 group. Okay? And the field strength, since the U1 group is abelian, the field strength that here it is. So since this is abelian, the Maxwell fields in this case are not matrices, so the commutator vanishes, and the only thing we have is F is the exterior derivative of A, or written in terms of tensors, the action for Maxwell. And during this series of lectures, I will be working mainly in Euclidean signature, okay? So there are some minus signs that in this signature become plus signs, like the one that goes here. This will be 1/4 d for x. In general, you can define it in curved space, so I will put the square root of g here. And this will be f mu nu, and this is the Faraday tensor, the Maxwell field strength, okay? And so this is the transformation, the U1 transformation. Let's say this is a gauge theory for the U1 loop. And in this case, the gauge connection transforms in the following way. Plus, and here, an arbitrary function. So you can obtain from here the Maxwell equations by performing stationary variations of this action with respect to the gauge connection. So the equations of motion will be this vary with respect to A, and notice that there are A's here, so you integrate by parts, and then equal to 0 will give you that these are the Maxwell equations, okay? Actually, in general, if you are considering or if you are coupling the Maxwell theory to your favorite gravity theory, for instance, GR, then the metric becomes dynamical, so you need to perform variations with respect to the metric as well, and you can define the stress energy tensor for the Maxwell fields, okay? But before doing that, now since these are the Maxwell field equations, and recall that the Bianchi identities were written in this way. And in flat space, this nabla is just partial. But in general, if we are considering general curve backgrounds, then we need to take the Levi-Civita connection, for instance, and this will be the derivative that transforms covariantly under general coordinate transformations. But notice that the Bianchi identity, I can contract both sides with the Levi-Civita tensor, let's say 1/2 mu rho lambda. And if you do that, and since the Levi-Civita tensor is covariantly conserved, I can put it inside of the derivative, and then I can write the Bianchi identity in a form which looks pretty much as the Maxwell equation, but for the dual field strength. So since these are the Maxwell equations, and this is an identity, you can see that, and the two of them will give you the whole set of Maxwell equations that you usually learn in electrodynamics, then you can see that they remain in vacuum. So I'm not considering sources here. But they are the same, but by interchanging F by F tilde, right? So this is the electric magnetic duality that electromagnetism has in vacuum. And this is no longer true if you have sources, okay? But something very interesting happens if the self-duality condition is satisfied, okay? Because these are the Maxwell equations. And so, we'll continue here.
So, I have a question.
Yeah.
Does this mean that any self-dual two-form is a solution of the vacuum Maxwell equations?
Yes.
Ah, okay.
Yes. And this is very interesting because I will explain this in the following. Oh, what happened with the other? Ah, okay. Well, I will leave it there then, because I will use it. So let me. And so consider anti-self-dual configuration. That's it. This is that F union plus minus F tilde union. Notice first that since F depends on first derivative of A, then you can see that the Maxwell equation is of second order. But notice here that this is a relation between the field strength and its dual. So this is a first order equation, and the other one is a second order field equation. But notice that if this condition is satisfied, I will plug this into the Maxwell equations. And this is what will happen. So I have this F union. I will plug this condition, so I will get plus minus F union. And now this is the Bianchi identity. So this is identically zero. So if I solve this condition, let us assume a particular metric, and I put a background metric, and I put some gauge fields on top of that, and I demand the self-dual or anti-self-dual condition, and I find, and I'm able to find a gauge configuration that satisfies this, then the Maxwell equations are automatically satisfied. Okay? So this is very important, and other interesting things will happen here. For instance, consider now, I will vary if we are in a gravity, if we couple Maxwell theory to a gravitational theory in GR, where the dynamical field is the metric, then I need to perform variations with respect to the metric as well. If I vary the Maxwell action with respect to the metric, this will give me the stress energy momentum tensor for the Maxwell fields. And in this case, the stress energy tensor. For Maxwell, can be written in this way, like minus 2 over the square root of g. So if I delta the Maxwell Lagrangian, I will put here the volume element, the Maxwell Lagrangian, and you divide this with respect to the metric, then you will obtain the standard piece that you, perhaps some of you are familiar with, 1 over 4 g mu nu f squared. But there is an identity.
Professor?
Yes.
I think the innocent question. You recently talked about general relativity. So if you want to do a relativity-like formalism,
Yes.
doing the variation of the connection, it's the geometrical connection or the gauge connection?
Good point. In general, f mu nu depends only in the of the partial derivative. You don't need to include the Levi-Civita connection or the Christoffel symbols, or as you want to call it. So variations of the matter Lagrangian, let's say of the Maxwell Lagrangian, with respect to the connection, won't give you anything. So the only contribution that you will get to the field equations are variations of the matter Lagrangian with respect to the metric in this case, but not with respect to the connection. This is not true in other cases, like in the Dirac case. If you consider the Dirac Lagrangian, this will depend on the connection, and so you need to perform variations with respect to the connection as well. This will give you the spin density that sources torsion and blah, blah, blah. But in the case of Maxwell, this is not the case. The derivative that you use to construct the Maxwell Lagrangian is the standard partial derivative, so there is no variations with respect to to gamma in this case, and this is the only thing that you will get. But this is not true for all matter fields. Okay? So what it is nice, and this is task 2. Show that, and this is an identity. You don't need to assume beforehand that the field configuration is either self-dual or anti-self-dual. What it is true is that playing around with contractions of the Levi-Civita tensor and blah, 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 you can write the Maxwell field strength in the Euclidean in the following way. 1/2 g lambda rho, oops, and this will be f mu lambda plus f tilde mu lambda f mu rho minus f tilde mu rho. So something very interesting happens if your configuration is either self-dual or anti-self-dual. Because if it is self-dual, this piece is equal to 0. So the stress energy tensor vanishes, even though the field configuration can be non-trivial. The same happens here if it is anti-self-dual. We'll cancel this piece. Have you ever heard about these stealth configurations in scalar tensor theories of gravity? No? Perhaps some of you. But in this sense, just a moment, in this sense, the anti-self-dual configurations in the Maxwell case resemble the stealth in the scalar tensor fields.
Is this true also in Lorentzian signature, or it just happens?
All right, now in Lorentzian, in Lorentzian signature, first of all, the dual, the definition of the dual, or let's say, the definition of the dual is always with epsilon contracted with the field strength. But the anti-self-dual or self-dual condition is defined with that imaginary in front. So in Lorentzian, in the Lorentzian, the same definition for, so let's say F tilde, F nu, 1/2 epsilon mu lambda rho, F lambda rho, and anti-self dual condition is F mu is plus minus I plus minus, sorry, I. This is the condition in the.
So if I want just a real mathematic field, I cannot have that.
This is the problem in the Lorentzian signature. But if you clear, you have everything is real.
If you use Hodge style, the I should be the definition of the dual.
Actually, yeah. So first, this is the definition of the Hodge. But if you would like that the Hodge acting 2 times gives you plus minus F, I do not recall what sign is, then you need this I for this condition to be satisfied. This is the problem with the.
Because if you act with Hodge style again, you shouldn't have.
Yes, this is it. Exactly. All right. There is another thing. How I'm doing with time, Nico? Is it Nico or Camilo? 45 again? Okay.
Okay.
Yeah.
It's a ignorance question. Why it's called stealth? Stealth configuration. Why is there
Stealth? Have you ever seen this? If you put stealth on Google, there appears these funny planes of the.
Yes, but why? Why in this case?
Yeah, because they do not gravitate in the sense that the TMU. So you could have field configurations which are non-trivial, like in the case of dions. There are self-dual dions which has non-trivial electric and magnetic fields. They are actually equal one to each other, but they do not gravitate. They do not back react. So you can take whatever metric you want, and your Einstein field equations on the right-hand side, the T mu will be 0. So it is like solving the Einstein field equations in vacuum, even though you have matter fields which are non-trivial in general. Because the T mu will be 0, but the fields inside are non-zero. This is in the case of the scalar tensor theories. This is what happens. So you have a T mu for a scalar field which is not minimally coupled with the geometry. And actually, there are some geometries with scalar fields on top, such that the T mu is vanishing, even though the scalar field is not here. Same here. So the T mu can be 0 for anti-self-dual or self-dual configurations. However, the F mu can be non-trivial. It can be the gauge connection is not pure gauge in this case. Okay. Yes. Royce.
How would we define charges in this case? What is the energy of?
All right. And this is what I will talk next. You do have topological charges, which are related, in this case, to topological invariants of the Poincare class.
Great question. I was going to ask basically the same. So if the
Right.
asymptotic ADM mass is zero or not in this case.
The ADM mass for the solution that you are considering in general is not zero because
Even if it is stealth, like even if it's not stealth
Yeah.
validated. Okay, that's
right, because even though the stress energy tensor can be trivial in this case, the ground state can be different, can be modified because the action could change, and so your ground state can be different in the presence of these topologically non-trivial solutions.
Right.
So I think you can, so you can have a stealth solution that does contribute to the ADM mass, but it doesn't. If the solution is a stealth, the ADM mass corresponding to the solution is always zero. It does not change the ADM mass of the gravitational background. Yes, is it true or not?
I think that at least in the case of the ADM mass, because the ADM mass you need to perturb, of course, the solution around a particular background. So, in the case of the ADM mass, I'm not so sure. What I'm sure is that the value of the action will be different in the case of a step. So, if you have, oops, thank you.
And what about background independent mass measures, like the usual ones, like I don't know, like is it zero or not? Like is it the mass of the solution is zero or not? If it's a step. Yeah. I also don't know. It's a very interesting question.
Yeah, there have been some papers
Uh-huh.
super recently
Uh-huh.
because what it is known is that at least the value of the free energy is different.
Uh-huh.
So one would expect that the value of the mass and your thermodynamical quantities will change in the presence of these kind of configurations.
Uh-huh.
So this is true. But what about the mass and the other kind of things? I'm not completely sure about that because is some ongoing research by now. At least in the case of scalar tensor theories.
Right.
Because even though this bulk stress tensor will be zero in ADS, the boundary stress tensor will be different. So I can compute the sharpness using
Sure.
that quantity.
Yeah.
But it's still a little.
No, but if you compute, for instance, if you are in GR and you would like to compute the boundary stress tensor for, let's say, a charged black hole, which is charged with self-dual configuration, so you do not, you cannot see the back reaction of this at the level of the metric, then the boundary stress tensor, at least in Einstein-Maxwell theory, will be the same due to the fall-off of this configuration. But I'm not sure in general, to be honest. This is an interesting question to look at.
Sorry.
Yes.
When you're in the self-dual, the mu is zero. At
Yes.
the classical level. On the
Yes.
quantum level, you should have there is anomaly, maybe not zero, right?
That's true in yes, at least in 4 dimensions, the Maxwell field is conformal, so at the classical level the trace is equal to 0. And at the quantum level, you could have the trace anomaly. This is true.
But this implies that the mu is not zero at the quantum level, or is there an anomaly of this?
In general, there are anomalies, but I'm not sure if you can, because some of these configurations are topologically protected. Okay, they have non-trivial topological charges, which doesn't allow you to go from this particular sector to the trivial vacuum. You cannot deform it continuously into the trivial vacuum. In the case of anti-self-dual configurations, what happens with anomalies in that case, I will talk about that in the case of the axial anomaly, and we will see that actually they do contribute to the axial anomaly in this case. And I would say, because in the case of the anomaly for the Maxwell field, the trace of the stress energy tensor is proportional to F squared or some power of the field strength. And so if it is proportional to F squared, if your solution is self-dual, F squared is like the Montiagin density. So the integral of the trace anomaly, I would expect that it will be proportional to some Chern numbers or the Montiagin numbers, because it will be the integral of FF dual. So this is sort of consistent with the sense that the trace in the conformal anomaly, the trace of your stress energy tensor has to be proportional to some conformal invariance. The same way that you have in the axial anomaly, they have to be parity odd. So yeah, so at the end of the day, the integral of the trace anomaly in that case will be proportional to the Chern-Pontiac index in that case.
So it's like a topological charge.
It should be a topological charge. Okay. What else? So let me show you another thing in the case of Maxwell theory. So the Maxwell action was 1/4 or x g f mu. And so you can write this in the following way. So this will be 1/8 m p for x square root of g. And I will put here f mu plus minus f mu tilde and I will subtract the cross term, and this is, so this goes with the minus plus 1/4 for x square root of g, which is f mu. And this guy it is defined as the Chern-Pontiac index of this connection. It is a topological invariant. It doesn't depend on the metric, and it is defined in this way: y squared minus square root of so you can put this on the left-hand side. Plus minus 4 pi C2A x square root of g. Or put it squared, which means exactly this. Okay? And since we are in a Euclidean signature, the right-hand side is positive definite. So this can be and the bound is saturated exactly for self-dual or anti-self-dual configurations as well. So if your field configurations is either self or anti-self dual such that this term cancels, then you will see that the bound is saturated. And this is the lower value that this action could have. So if this way. Then the action is proportional to a topological invariant, which is called the Chernkov-Dragin index. And so it is possible also to modify initially the action by adding the Chernkov-Dragin term, fixing the coupling such that this term is absent, and therefore you can sort of enlarge the ground state of the theory to all self-dual or anti-self-dual configurations, and not only to pure gauge or trivial configurations. So this is the idea. You just modify the action by this topological term. You won't modify the field equations because it can be locally written as a boundary term. However, you will change the value of the action and variations thereof, also the charges. And in that case, you will see that if you add with a very particular choice of the coupling, it is like canceling this piece, and therefore the Maxwell action will be 0 for anti-self-dual configurations. But I won't do that. You will have it in my notes. I will send you my notes. But this is, at the moment, just a comment. Okay? Okay, so let us discuss some solutions to Maxwell equations in this tab. For instance, how much time do I have? Or perhaps 25. Perhaps I should jump, because I also have the discussion of the magnetic monopole. In the case of Dirac, there is the nice quantization condition, but perhaps you can take a look at it later on. Let me discuss how these work in the case of instantons, and perhaps we can discuss a particular type of instanton, like the one found by Bela and Polyakov and friends back in the 70s. So let us discuss some of these properties in non-abelian gauge theories.
May I ask a question? Because
Sure.
I'm very curious. So, your statement that this T minimum, because before you go to another case, does not produce right-hand side in Einstein equation.
Yeah.
Is for this you need that one of these factors gets 0, right?
Yeah.
And this means physically that either you have electric field equal to magnetic field,
Yes.
or you have electric field equal to minus magnetic field.
Yes.
And since we know that any electromagnetic field can be represented as a superposition of waves, plane waves, this is impossible. Because we know in the plane wave, you have all this electromagnetic field orthogonal to magnetic
Yes.
field. So I think it can never be 0.
That's an excellent question, because in the case of electromagnetic waves, if you write the F mu nu tilde F mu nu, this is, as you were saying, proportional times B. So for electromagnetic waves, this cannot happen. But if you have some other, like other sources in your media such that this is different from zero, in that case, this won't need to be zero in general. This could happen in curved spaces, for instance, and in some particular materials.
Yes, but they never get parallel. In media, I don't know, but in curved space, I'm almost sure that I cannot get it.
Okay, no, but in curved spaces, I think that there is some analogous to what happens in media, such that this effect could happen. If you are let me think. Because if you have topological defects, for instance, like in the case of the magnetic monopole, this won't be zero either. But
not zero.
It won't be zero, yeah. But this is because you have removed a particular point in space which could have a topological defect, like the Dirac string or something, and this particular combination, this f tilde f, won't be zero in that case either.
Okay, I think we're good.
We can discuss it later. But there are particular cases, and in general, some of the solutions, like in the magnetic monopole, this is something that won't happen in dions. This is different from zero. In the case of electromagnetic waves, this is zero. For radiation in general, this is zero. So I agree with you in that case. But for other topologically non-trivial configurations, don't need to be. But we can discuss it later. So let me discuss a little bit the case of SU2, Yang-Mills theory. Any other questions?
In the case of the ionic Reynolds nostrum, that is not zero?
In the case of the ionic Reynolds nostrum, no, it is not zero. But in the electric one, it is zero.
So just a comment maybe. So the case with the electromagnetic materials where something like this can happen, is when you have, let's say, axion electrodynamics, right?
Yeah.
So you can add an explicit Chen-Pontryagin term for the Maxwell field, and basically this is a model, it's a theoretical model of what can happen when you have a magnetoelectric effect, for instance, that you have a magnetic field that can source an electric field response, and vice versa. So this actually can happen in materials that exceed certain topological order, like the quantum Hall effect and things like this. This is actually real material science. But okay, so the meteoroscopic theory is whatever, non-standard quantum Hall effect. This is the real physics. But then as a toy model of this phenomenon, you can model it in terms of an axion electrodynamics system, and there basically you're doing this. You're adding an explicit non-zero Chen-Pontryagin term to the Maxwell action.
Right. In that case, the axion.
You have a non-trivial theta vacuum, but for the electromagnetic.
Yeah, in that case, the axion though is non-minimally coupled to the Chen-Pontryagin term.
Okay.
So if
there is a non-zero theta vacuum, but you don't model it like a field, like in the Peche-Quinn effect.
Yes.
Truly, you just model it like a step function. Like inside the
topological
material,
insulators.
yeah, exactly. Like inside the material, the theta values whatever, and then outside the material values whatever.
Right.
Right.
Yeah.
This is actually true. Like you can do it. Materials have been constructed to have this problem.
Yeah. So due to this, I have the same impression that a very similar phenomena could occur in gravity as well, and also in the presence of topological defects. All right. So let us discuss what happens in SU2, Yang-Mills theory.
Professor?
Yes.
The stress energy momentum tensor that is obtained with respect to varying to the metric Is the same that one will get if one were to apply Nether's theorem?
Good question. In the case of the Nether theorem, I think that then you need to modify a little bit the transformation of the gauge potential with respect to coordinate transformation, because you could get a piece that it is not gauge invariant. But I think that it is possible if you modify the transformation such that you get exactly this one.
Okay.
Yeah.
You can always modify it by adding the Infante tensor.
Yes.
That you can always do.
Yeah. You know the Belifante theorem?
I don't remember the form, but yeah, I've seen it in
We can discuss it, but it is always possible to introduce an additional piece such that you get the correct stress and energy tensor as you would get in the gravitational case. Okay. So in SU2, Yang-Mills theory, very interesting things happens because the theory is non-abelian. And now I will use the following notation. The generators for the SU2 group will be Ti minus I over 2 tau I, where these are Pauli matrices. So with these choice with the I and with the minus, these are anti-self-adjoint, okay, anti-emission generators of SU2. Okay, so in this, with this definition, they satisfy the Lie algebra okay. The anti-commutation relation is Ti Tj Ij 2 by 2. And there are other relations that I won't write. And it is very convenient in this case, and I will use it throughout my lectures, to define the left invariant forms. Left invariant forms, which will be parameterized in terms of the Euler angles. This will be sigma 1 psi d theta plus sin theta psi d phi, the sigma 2 minus d phi and sigma 3 okay, one here. And the left invariant forms satisfy left invariant forms of SU2 satisfy de Mourier Cartan equation, which is this one, plus equals 0. And actually you can parameterize the metric of the 2-sphere and the 3-sphere by taking these objects. For instance, the standard metric of the round 3-sphere, of the round 2-sphere, which is can be written as sigma 1 squared plus sigma 2 squared. And the metric of the round 3-sphere can be constructed as the Hopf vibration over omega, the 2-sphere, which will be this 1/4 is in order for the metric to be round, to be the unit metric of the unit 3-sphere plus sigma 3 squared, okay? Which will be exactly this plus this other term squared, okay? So, in the case of Yang-Mills, the action the Yang-Mills action is will be minus 1/2 for x root of g, and now the trace is taking over the internal indices of SU2. Okay? And the equations of motion, as usual, you perform stationary variations with respect to the non-abelian gauge potential, and then the field equation will be this one. Which now is a second order but non-linear field equation. So it is far more difficult to solve. Okay? In the case of Maxwell fields, it was a second order but linear equation. So the superposition principle and everything else that you learn in electrodynamics works perfectly. In this case, you cannot use the superposition principle in general. So you cannot use it.
Why not just write it the covariant derivative of F mu equal to 0? But now understanding that the covariant derivative is also colored under the gauge loop, that is already the adjoint. I mean, it's at the end of the day, it's a null curvature equation.
That's a good point. Actually, I could put here the D,
yeah.
But in my notation, D was only with partial.
Right, so you need to extend it. Right?
Yeah, it's just to be consistent with my notes. But you're right. So this is the covariant derivative of SU2 in the adjoint representation. Yes. And actually, you can also compute the stress energy tensor in this case, and you will see that it looks pretty much as in the standard Maxwell case. I will write it like 2 trace, where again trace is taking over the internal indices, lambda f nu lambda minus 1/4 g mu f squared. And you can see this is task 3, that again can be written g lambda rho f mu lambda plus f tilde mu lambda f mu rho minus f tilde mu rho. So exactly the same argument as I was explaining in the Maxwell case applies here for self-dual configurations in the non-abelian sense. Okay? And additionally, the very same thing also in the case of Maxwell theory, namely that anti-self-dual or self-dual configuration automatically satisfy the Maxwell equations. In this case, will happen as well for the Yang-Mills case. So if you are able to find self-dual configuration in the case of Yang-Mills theory, then it will solve automatically the Yang-Mills equation. And this is what the people usually do, at least in the case of instantons. In order to obtain an instanton, we do not solve the Yang-Mills equation, because it is super difficult. It is second order, non-linear, blah, blah, blah. But in the case of the self-dual condition, okay, it's non-linear, but at least it's of first order. And this is easier to solve. And I will show you an explicit example, a particular solution that it was found by Bela, Polyakov, and friends in the 70s by integrating the anti-self-dual condition, and therefore it automatically satisfies the Yang-Mills equation. And this solution has non-trivial topology, as it can be checked by computing the Cherpon-Triagon index for the non-abelian connection, and it has topological charge equal to 1. Yeah?
Sorry, where did you use the left invariant forms?
I will use it now. So, the BPS, Bela Polyakov charts and Tubkin instanton is the following. So, you can assume an ansatz for the metric, but the metric will be, we will solve the equation in Euclidean four-dimensional space, but I will write it in this way, like so this is the metric of R4. And for the Maxwell, for the Yang-Mills fields, I will assume a particular profile that will depend on the radial coordinate. And I will take the left invariant forms contracted along the generators of the SU2 group. And I'm not going to solve this equation. I will solve the following equation. We take these two and plug it here. If you do that, you will get a first order field equation for the profile A. And this equation is R A prime plus minus A 2A 1 minus A equal to 0. And so there are two equations, one for the plus and one for the minus, and therefore there are two solutions. And these are then the solutions are squared over, and this is for the plus, and the other one and this is for the one with the minus.
I'm sorry,
Okay.
where did we get this metric?
This is the, okay, so this is the metric of R4. So this is the metric of Euclidean four-dimensional space. So this is R4. This is a particular parametrization.
It's a hyperspherical coordinates.
In hyperspherical coordinates. But it is the metric of R4. If you compute all the components of the Riemann for this metric, all of them will be 0. This is the flat metric, nuclear space. So if you take this and solve the self-dual or anti-self-dual conditions, you will have these two solutions. Okay? And there is something nice here. One of these solutions, this one, the profile, goes to 0 asymptotically. This one. So the gauge potential is trivial as R goes to infinity. The other one is not. The other one, A, goes to 1 as R goes to infinity. Okay? So the potential is pure gauge, as you can check by using the left invariant forms of SU2 and convincing yourself using the definition that I gave before, this one. F is dA plus A wedge A. And you plug that one and put here a 1, use the standard relations that I gave, and you will see that if A is equal to 1, then capital A is pure gauge. So this solution is asymptotically pure gauge. So the solution is asymptotically flat in the sense of the field strength, of the non-abelian field strength. Okay? And since this guy has one leg, one index on space-time, and another index on SU2, they are mappings of the space-time. In this case, asymptotically, the boundary of R4 is S3. So asymptotically, this solution represents a map from the 3-sphere into SU2. And these mappings are labeled by topological indices. actually you can compute what is the term-Pontryagin index of this configuration. First of all, this is a regular solution. You can check this by computing your favorite invariant. For instance, could be this one. And we construct the solution such that it is self-dual. So two things will happen. The first one is that, as I was explaining in the case of Maxwell fields, the action will be proportional for the, if f mu, if this happens, which is the case, this will be proportional to the term-Pontryagin index of this configuration. Additionally, you can compute this invariant, and you will see that gives you, lambda is an integration constant. You only have one integration constant because it is a first order differential equation. So this is usually called the instanton size. In this case, the trace is minus 96 lambda 4 over r squared plus lambda squared to the quartic. So it is regular for all values of r. And you can compute the action for this particular solution, and it gives you the minimum value for this particular homotopy class, which will be 8 pi. So let me summarize here. So in this case, the action for the BPST instanton will be 8 pi squared, and the term-Pontryagin index that you can compute it as well for the two solutions is plus minus 1. That represents the topological charge of this configuration. So it has winding number equal to plus or minus 1, which is related to the mapping of the 3-sphere into SU2 asymptotically. Okay? So I think I ran out of time, so thank you guys. Opalo has
Capital A is a 1/4 in R4.
yes, this guy is
How can you have a DR?
good question. No, because I'm only considering the pieces. These are particular ansatz, so it is a sort of magnetic kind of ansatz for the Yang-Mills field. Actually, you could have another one. I could have considered an additional piece like BR, DR. This is pure gauge, because if I take the exterior derivative, it will give me VR wedge DR. This is 0, so this can be gauged away. But actually, you could consider another dependence here, like theta or phi or whatever. And this, in principle, will be non-trivial. I haven't heard about this kind of instantons, to be honest. But the one of VPST is only with this part.
This theory is conformal invariant.
Yes.
So, a conformal inversion, you are mapping the self-dual solution to the anti-self-dual solution. Because if I change it, R goes to 1 over pi, so the one goes to the other, one solution goes to the other. No? Because 1 is 1 at r equals to 0,
Yes.
and 0 at r equals to 2. And the other one is exactly the opposite.
Right.
So it seems that if I do a conformal inversion, I'm mapping 1A to the other.
That's a good point. I haven't noticed this. Yeah, perhaps there is a duality between these two, like, or a conformal transformation that will be one in terms of the other. I have no idea, to be honest.
So thank you all for coming and